Oh, wasn't all by choice. Thanks, Carsten, for the introduction. Oh, I think I'm a little bit loud. Let's see, can I turn this? Gain. All right, let's try this. Okay, is this better? Yeah. Yeah, so thanks, first of all, for putting together this really fantastic event and all the work that the Penn State group put into this. It's really a great event, and it's always lots of stuff to learn, so I really enjoy being here. And so I'll try to do my best to explain to you this morning magnetic circular dichroism. It's a kind of a hard nut to crack right at 9 o'clock in the morning, but let's get to this. So just like you see with the other presentations, kind of the same outline here. We start thinking about the theory of magnetic circular dichroism, understanding what's the experiment, what are we doing, and then from there we'll transition into some examples. And in my lab, we do a lot of work on metalloporphyrin, so you can see my examples here are kind of biased in that regard. We're looking a lot of metalloporphyrins and their MCD spectra. So I always call MCD the sleeping giant, right? I like this picture here. And because MCD is a very powerful technique, but it's also quite exotic, so it is not really that widespread, not that often used, but there's just a lot of information that you can get from MCD spectra, spectral resolution, but also you can optically detect magnetic saturation curves. You can get information about the magnetic properties of your ground states. You can get polarizations of your optical transitions in samples of randomly oriented molecules. So without single crystals, you can do something like single crystal spectroscopy. You can get polarization information. So there's just a lot of unexplored potential. So MCD is still a sleeping giant, so I hope I can help this morning the giant to wake up and rise, and maybe you guys get interested in using MCD for your own research. So the whole thing goes way back into the 1800s to Michael Faraday, who discovered the so-called magneto-optical effect. Right? So if we take linear polarized light, indicated here, so this is the electric field vector of our light wave, and it oscillates here in this plane, so it's linear polarized light, and we shine this through a medium, and now we apply a magnetic field, a longitudinal magnetic field. So you can see here the magnetic field lines, they are parallel to the direction of propagation of the light. You turn on the magnetic field, and you can see that the direction here of linear polarized light rotates. So the angle rotates a little bit, and that's the magneto-optical effect. Now, in order to understand this, we need to learn a bit more about linear polarized light. So linear polarized light actually is a superposition of two beams of circular polarized light. One is left circular polarized, the other one is right circular polarized. And then if you superimpose them, you end up getting linear polarized light. So I hope I'll be able to explain this to you. Here's a picture of a circular polarized light wave. This is left circular polarized light. So if you're standing on this side and the wave is approaching you, and you can now see the electric field vector of the wave like is rotating while the light is propagating. So you get this helical motion. And now if you're standing here watching the beam approach you, you can see that the electric field vector rotates counterclockwise. And that makes it left circular polarized light. So now if we take a wave of left circular polarized light, a wave of right circular polarized light, so you can see this here on my diagram. So one of this is electric field vector. One wave rotates this way counterclockwise, the other one rotates clockwise. Now we add these vectors up, then we end up with something like this. And now as these two field vectors move now in phase, they move down. You can see when they get to this position, they exactly compensate each other. So the blue vector here goes to 0, and then as they go further down, it goes negative, and then it oscillates up and down. So indeed, if we superimpose these two waves of left and right circular polarized light, we end up making linear polarized light. And so this is kind of the way to think about this. And so then when we now shine this light through a medium, we apply a magnetic field, right? What we do is we actually change the phase between these two circular polarized light waves, and this is how we make the linear polarized light move. So essentially what happens then is that the left and right circular polarized light wave, they propagate at different speed through that medium in the presence of the magnetic field. Right? And so if you offset them a little bit, one goes faster, one goes slower, you change the phase between them. That means when you add them up, they maybe don't. So we can also call this the real part of the refractive index. So the requirement for this is that the medium does not absorb the light. Right? So the only thing the medium does is, in the presence of the magnetic field, it changes the speed of the light waves as they pass through, but they're not absorbed. So this is the assumption for this effect. Now, an interesting part is if we now move on, and what happens if there is a difference in absorption? So if the left and right circular polarized light are absorbed, but they're not absorbed in the same way. One is absorbed more than the other one. And this is a cute experiment because it also shows you that this concept, again, of thinking about linear polarized light as being the superposition, this concept is maybe not so far from the truth, because if we do this, we can generate elliptically polarized light. Right? So how can we think about this? Well, if we now go back to our picture, and we have our light waves passing through our medium, but now we absorb, and in my case, I am absorbing the right circular polarized wave more than the left circular polarized wave. So you can see my amplitudes now are different, right? They're not the same anymore. So you can already see what's going to happen, or they're not going to cancel each other out anymore, exactly. So in this position here, if I add them up, I end up with this superposition here. This is the resulting electric field vector. Now I'll let them rotate, and then if I go to the critical position, 180 degrees, right? Before that, this exactly cancels to 0, but now there is a residual field component here. And so if I follow now this blue vector here, as it moves around, it gives me something that looks like this. So I go from linear polarized light to elliptically polarized light, right? By just absorbing the left and right circular polarized light beam in a different way. They add up like this. And this is a nice demonstration that maybe this model, right, this model to think about linear polarized light is not so far from the truth, because otherwise, how do you explain this? Right? How do you explain to go to elliptically polarized light? So what we want to do, of course, in MCD, then we want to absorb light, so we're going to make use of this, and we'll get there in a second. So we can also say that this is the imaginary part of the refractive index, so it requires absorption of the left and right circular polarized light, and this is a form of magnetic circular dichroism. Right? So this is kind of the effect as it was discovered by Michael Faraday. So now you might say, well, that's all nice and pretty interesting, right? But can we actually do anything with this? In our daily life, is this going to help us solve some problem in the lab for some metalloprotein? And hopefully I can show you that, yes, we can make use of this more than just in this kind of interesting physical effect that Michael Faraday discovered. And so here's just a little bit of the fundamentals, what we do in an MCD experiment. So essentially we do a CD experiment, so we measure circular dichroism. Right, so the difference in absorption between left and right circular polarized light, just as I just explained to you. So you can just write it like this, so either delta A or delta epsilon if you do it in molar quantities. So the difference in absorption between the left and right circular polarized light. And you can write this out in the form of a Lambert-Beer law. Instead of an epsilon, now you have a delta epsilon, because it's a difference in absorption. So this is a CD experiment, and now again, we do this in the presence of a magnetic field, so this gets us from circular dichroism to magnetic circular dichroism, just like Michael Faraday did this. So, and then we apply the longitudinal magnetic field, and we usually do this at low temperature, and the reason why we do this will become clear as we go and look at the theory in a bit more detail to understand what are the different contributions that we can observe for MCD intensity. So, now we do kind of a fast forward from 1845 to about the 1970s, when P.J. Stevens, he was actually kind of the person who really got magnetic circular dichroism going in the kind of physical inorganic, physical chemistry community, and he is the one who worked out the theoretical framework for MCD spectroscopy, and that's still the way we think about this these days. So this is really here the foundation of the field, the way we use MCD now. So here's the experimental setup. The experimental setup is not that complicated. We just need these two components, the CD and the magnet, and we need to bring them together, right? Just like in Michael Faraday's experiment. So here's our CD spectrometer. Now it looks a bit more sophisticated. And then here is the cryomagnet. And we need high magnetic fields. in order to do magnetic saturation studies. So this magnet needs to go up to 7, 8, 9 Tesla, depending on what you can afford. And so these magnets require usually liquid helium, right? So they have a superconducting coil in them, so you can get up to these really high fields, which means MCD, especially these days, is not a cheap experiment, since you have to fill in a lot of liquid helium into your machine to run your magnet, right? So essentially you have this cryostat here, which contains a superconducting magnet and has an optical tailpiece on the bottom, so you can shine your light through your sample that sits in the cryostat, and then at the same time you can change the strength of the magnetic field. So liquid helium temperatures are required. Now, Oxford is kind of the number one company who builds these kinds of cryomagnets, but they're not really good in shielding their magnets very well. So there is a very strong stray field, which requires now that you put a little bit of distance between your sensitive spectrometer and your detector and the magnet, right? So you might wonder, why is there this strange setup built out here? It's just because to space this out a little bit and to have less of an effect of the magnet on your spectroscopic equipment. So we have about 1.5 meters here between the CD, then here is the magnet, and then the detector is about another meter away, and that's just because of the magnetic stray field that comes when you ramp that magnet up to 7 Tesla, which is a pretty strong field. But that's the setup, so not too complicated. And so let's go on now and talk a little bit about the fundamental or the theoretical framework of MCD spectroscopy. So this is the kind of the master equation that was derived by P.J. Stevens in the 70s. And if you just look at this equation here, just with an innocent eye, you can first identify there are 3 different contributions to the intensity, which he just called the A, the B, and the C term. He could have also called it the apple, the pear, and the orange. So there is no further really information content in the labeling here, A, B, and C term. And then we have, so E here is just the energy of the light. We have a function of E. This is an absorption band shape. So this F of E here and here, this is an absorption band shape. So in the simplest case, you can approximate this as just a Gaussian function. So F of E is an absorption band shape. And then this one here is a derivative, first derivative with respect to energy. So that would give you kind of a derivative band shape. So you can see that these are 2 different types of signals that are apparently observed, where the A term gives rise to this derivative shape, and then the B and the C term give rise to an absorption band shape. You also notice that of these 3 contributions, only the C term has a temperature dependence, right? So if you look at where is T in this equation, it's right here. So C term is temperature dependent. And then finally, you see that these intensities are linear with field. They're directly proportional to field. So that means if you double your field, you should double your intensity. And based on this equation, you could just drive this on to the moon, so it will go forever. And as we will see later, though, that is not entirely true. So for the C term, you will actually observe saturation at some point. So there is a region where this equation is valid for the C term, and then another region where we will see saturation. And we'll understand in a little bit why that is. But this is kind of the general framework here of the theory, assumes that this is all linear with field. Okay. So if you just focus on the C term, then this is also interesting. And this kind of sets the tone here to kind of see whether a relation is to magnetism, right? If you look at the C term and the temperature dependence of the C term, so if we just isolate this out of the equation, you can see intensity is proportional to C over KT times beta times B. And if we just assume, let's say the field is constant, so we set the field to a certain strength, Tesla, and keep it constant, and then we just vary the temperature, we get an equation that looks just like a Curie law. It looks like we're measuring magnetic susceptibility. But of course, we're measuring optical intensity, right? We're measuring a CD signal. So what that implies, if we follow the CD signal as a function of temperature and field, we'll get something like a magnetic saturation curve. And that is, in fact, the case. So with MCD, we can optically detect magnetic saturation curves. So you can see this from kind of the framework here of this equation. So if we just look at the Curie law, then just as a kind of a reminder, right? So if we plot magnetic susceptibility against temperature, right, we get this 1 over T kind of behavior. And so the C term intensity will behave in a similar way, just fundamentally because it has the same overall setup as the Curie law. So we get back to this in a little bit. Okay, and so finally we should quickly introduce the MCD selection rule, which is important. And so if we take just an example here, so this will be a simple S equals 1/2 spin system. So let's say it's a copper 2 complex with an S equals 1 ground state. My ground state here, then if I apply a magnetic field, I will split it into the 2 magnetic sublevels, and we've heard a lot about this in the EPR talks and also from Eckhard Mürk in the Mössbauer talk, right? So we get these 2 sublevels, and then the same thing happens in our excited state here, assuming this is also a doublet excited state. So we split these up in the magnetic field, and now we can have 2 different types of transitions. If you look at the change now in the magnetic spin quantum number, it can either be +1 or -1, and that's where the MCD selection rule comes in. So the selection rule says that the absorption of left circular polarized light requires a change in the magnetic quantum number by +1, right? So this will be the red line here. And the right circular polarized light leads to a change in the quantum number by -1. So that will be the blue transition here from +1/2 to -1/2. So we have 2 transitions. One is induced by absorption of left circular polarized light, one absorption of right circular polarized light, and this is the selection rule. Okay. So let's go on then and look at these 3 different intensity mechanisms to understand a little bit better where they come from and what the implications are, especially if you're thinking about diamagnetic versus paramagnetic systems and what that applies to. So first is the A term. So the A term requires a degenerate excited state. And we'll see in a second why that is useful. And if we look at just this equation here, and so this equation is written out for a transition from a ground state, which is called A, and we transition into an excited state we call J. This is generally the way I have set this up here. And then for simplification, we're just looking at this as kind of a one-dimensional case. So the light only propagates in the Z direction, and that, of course, remember, this is also the direction of the magnetic field lines. They are parallel to each other, right? So we're kind of looking just in the one-dimensional Z case here for simplification. So kind of to understand just the basics, what's going on. So you can see then in this intensity expression here, we have 2 components, right? We have a Zeeman part. So you can see here L plus 2S, the Zeeman operator applied to the excited state, applied to the ground state. So these are splitting this up into the magnetic sublevels. And then here's an electric dipole part, where we have electric dipole transitions between our ground state and our excited state. But if you look at the electric dipole operator here, this is not the normal mu x, mu y, mu z. This is mu minus or mu plus. And so these are actually the electric dipole operators for the linear polarized light. And so you can see how they're defined as a linear combination, essentially, of the x and the y direction. So remember, the light propagates in z direction. We can only induce transitions that are polarized in the x or the y direction. So orthogonal to the propagation direction of your light beam. And this is a general property of MCD. So the selection rule is already pretty complicated, as you can see. So we can see that then the mu plus operator here, so the one for the left circular polarized light would be mu x minus I mu y, and then we have the corresponding operator for right circular polarized light. And you can see we're taking a difference here. So this is where now the degenerate excited state comes in. We need to have 2 components in our excited state. One that's x polarized, one that's y polarized. So 2 transitions. And if there's only one, then this will cancel out to 0 and the whole thing is gone. Right? So we can draw this up. Maybe then this will become a bit clearer if we put this kind of in a very simple energy diagram. Right? So the simplest case, the A term, does not require that the ground state has any degeneracy. So the ground state could be non-degenerate. The excited state is degenerate, and this could either be spin degeneracy. This could also be angular momentum or orbital degeneracy. And as we see later, this works actually pretty well for metalloporphyrins. So metalloporphyrins have degenerate excited states, and that's why they give, even if you make a zinc porphyrin, it will still give an MCD signal because it will give you an A-term signal because of this fundamental property of having orbitally degenerate excited states. So it's just a general case of a delta M. So you can see if there's no magnetic field, these 2 components have the same energy. And so now we have 2 transitions, one induced by left, one by right circular polarized light. But remember, in CD or MCD, we measure the difference, right? Now this is a degenerate state, so that means the extinction coefficient for these two subtransitions here is exactly the same. So without a magnetic field, they have the same energy and same intensity. So if you take the difference between red and blue, you end up with green, or in other words, no signal at all. So no magnet, no signal. Now what happens now if you turn on, if you ramp up your magnet? Right? If you ramp up your magnet, you will now start to split that excited state here into the magnetic sublevels. They will separate as a function of the magnetic field. So this is shown here. Right? So nothing happens in the ground state, but you can see now that the energy is now offset. So the red transition here is at a higher energy than the blue transition. The difference, though, is not very large, right? Remember from EPR spectroscopy, this part here isn't really that big. So it's a slight offset. But if you look at this then and you take the difference, you end up with this very, very tiny derivative signal. And even this, I totally blew this out of proportion here, so it's very, very small. But it gives you an MCD signal, and it has a derivative shape. So that's because the extinction coefficient itself for these two components is the same, but they are offset in energy, and then you end up with this signal. And apparently, since the ground state doesn't have to be degenerate, this actually works for diamagnetic compounds. And as I said, metalloporphyrins are a very nice example where you can observe these types of signals. They're weak, but you can measure them. And I have an example for this later in my talk. So this is the A term mechanism. So the B term is the one that looks most complicated, but in a sense the B term is a variation of the A term. Well, now we do not require anymore that the excited state is degenerate, so we could have a non-degenerate excited state, but as we've seen before, if we have a non-degenerate excited state, we don't get intensity, so we need another state, an auxiliary state, which we call K. So again, we're looking at the transition from A to J. Again, the magnetic field is in the Z direction, so we're just looking at the Z component. But now we have an auxiliary state K that is close to either the excited state or the ground state. And the important part now is that the Z-man operator, so under the magnetic field, we induce mixing between this auxiliary state K and our other excited state, J, that we're looking at, or K and the ground state. And these are the two parts here of this horribly long equation. There's one part, and you can see this here. This is the Z-man part, so here you can directly see it. This part is the one where we have magnetic field-induced mixing between J and K. And here's the second part where we have magnetic field-induced mixing between K and A. These are just two different possibilities, right? The auxiliary state could be close to the excited state we're looking at. It could be close to our ground state. In either case, if we can now induce mixing with the magnetic field between the states, we will again get MCD intensity. And you can also see here that the intensity scales, of course, with the strength of this coupling, but the intensity also scales with delta E, just as it is typical in perturbation theory. Of course, this is derived with perturbation theory. You can see it in the way the equation is written. So the further these states are apart, the weaker the coupling will become. It scales with delta E. So we can, again, look at this by using my picture here, my state diagram, which makes it, I think, more easy to understand what's going on. So this is the example here. This is an example for the first part here of this equation, so where we have mixing between J and K. So again, we're looking at the transition from the ground state A to the excited state J. That's the transition we want to measure. And then we have this auxiliary state K that comes in, and both of these are non-degenerate. So in the absence of a magnetic field, if the magnetic field is 0, right, then there is no mixing between these states, which means this integral is 0. If this integral is 0, everything's gone, right? So no magnetic field, no mixing now, no intensity. For the A term, no magnetic field, no splitting, no intensity here, no magnetic field, no mixing. Again, nothing happens. So we've got to have the magnetic field. If the magnetic field is able to mix these two states up, now we'll get our MCD transitions, left and right circular polarized light. Now, if you look at the difference, right, these are two different states, J and K. They have a different nature, generally speaking, which means that the extinction coefficient for the red and the blue transition are different. So that means our bands here have different intensity. If they have different intensity and we take the difference between them, we end up with this green line, which is an absorption band shape. Right? So in the A term, we're looking at the degenerate state with two components. That means the transition from the ground state into these two components has the same extinction coefficient because it's the same state, just the two different components, two different directions in space. Here we have two different states with a different nature, so generally speaking, they will have different extinction coefficients for these two transitions, and so we end up then with this kind of picture. So the B term gives rise to an absorption band shape because of this general property. Okay. So, oh yeah, and then just as a reminder, I've already said this, but I want to really stress this, that both the A and the B term intensity is linear with field, and that actually generally applies. So these intensities will never saturate, and as you keep ramping up your field, these intensities will always go up. They will not saturate. And then, of course, the B term also works for diamagnetic compounds, right? So again, there's no degeneracy here in our ground state. We don't need that, and that means it could be a diamagnetic compound. But what we need now is these two states that are magnetically coupled. And B terms, A terms, and B terms are weak, and they're not very often observed, especially if you look at metal sites in biology, non-heme iron sites, copper sites. They oftentimes have a low symmetry. So for these kinds of sites, A and B terms are usually essentially zero. They're negligible in intensity. So the really important one for us, and that's the one we're going to talk about the whole time, is really the C term. But these signals are sometimes observed, and so it is important to understand their nature. And you can see now how you can distinguish them, right? So as you will see, the C term will saturate at some point. The A and the B term will not. And so you can tell, by measuring your spectrum, you can tell the difference between them from the temperature dependence. Okay, so the C term mechanism now requires that the ground state is non-degenerate. And if you think about this, there are two possibilities how this could happen, right? So it could either be a state that is orbitally non-degenerate, or it could be a state that is spin non-degenerate, or it could also be both, of course, at the same time. But now if you remember Frank Nese's lecture, there is something that's called the Jahn-Teller effect. And the Jahn-Teller effect a little bit comes to our help here, because essentially what the Jahn-Teller effect does is it quenches the angular momentum of the ground state. Or in other words, it removes the orbital degeneracy or the angular degeneracy of the ground state. And Frank talked about this in his first lecture on ligand field theory. Here's just one simple example that shows you how this works. This is low spin iron free. And if we have an octahedral complex that's low spin iron free, we can put our electrons into the d orbitals. In this case, we have all the electrons in the T2G type d orbitals, 5 electrons, and then that will give us a state that is threefold orbital degenerate, because you can write this down in 3 different ways, right? The single electron could either be in this box, the single electron could be in this box, or in this box. So just by looking at this, you can see this has to be threefold degenerate. And then if we use ligand field theory and the typical nomenclature that goes along with it, we will call this as a doublet T2G state, doublet D2G ground state in this octahedral complex. And this is not stable, as Frank was talking about. So we can distort now this complex and we can gain energy. And as you know from thermodynamics, every system wants to go to the state of lowest energy if possible. So if we gain energy by distorting it, it will distort, right? And if we distort this, we can end up with a situation like this. So we split up these 3 T2G type orbitals, a set of 2, a set of 1. We put our electrons in, and now you can see this state is no longer orbitally degenerate. There's 1 orbital of 1 electron in it, and we would call this now a doublet D2G ground state. So the angular momentum is quenched by the Jahn-Teller effect. And that's very important, of course, for magnetic susceptibility measurements. That's why you can analyze your squid data with the spin-only approximation. And it also applies now to us here doing MCD. If there is no angular momentum, then the only way you can get degeneracy in the ground state is spin degeneracy, which means you have to have a paramagnetic compound, right? So C-term intensity then is only observed for paramagnetic compounds. There are few exceptions where you can force a system to have angular momentum in the ground state. It happens, but it's very rare. So generally speaking, the C-term mechanism only applies to paramagnetic complexes. And this is, of course, what we're interested in. If we're looking at a ginormous metalloprotein and we want to focus on the paramagnetic center in there, What are the methods we can use to do this? We can do EPR and we can do MCD to selectively look at something that is paramagnetic. Okay, so here's now the equation. Again, we're looking for a transition from a ground state A to an excited state J. Just as before, again, we're just looking at a one-dimensional case where we're just propagating in the Z direction for simplicity. And you can see the two components again. So it's a repeating pattern, right? All these equations, intensity equations, always have two parts. They have a Z-man part and they have an electric dipole part. In the Z-man part, now you can see here we have the splitting of the ground state into the magnetic sublevels. And then here's again our electric dipole part. And again, we have light propagating in Z directions, and we need two transitions that are X and Y polarized, so orthogonal to the direction of propagation of your light and, of course, the direction of your magnetic field lines. This is general selection rule for MCD. And you can see now, well, if we have this, right, so we have magnetic sublevels of the ground state, we'll change the temperature, we change the Boltzmann population of them, and so you can get a feel now why this could relate to the magnetic properties of the ground state, right? Because we're having magnetic sublevels, we're changing their population, and that will change as a function of temperature and field. Of course, temperature, right, because it's a Boltzmann distribution, and field, if you increase your field, you split the lines more, and you change the Boltzmann populations then. So you could see how this now could relate to something like magnetism from this point of view, right? So the magnetic properties of the ground state now are important for the C-term mechanism. And they have not been important for A and B term. So here's just the same thing now, our example. This is a little Gedanken experiment to kind of always challenge you to think outside the box here, right? So if we look at the C-term mechanism, but we would assume that we could actually do this at something like room temperature, which, of course, at room temperature, because of the 1/T relation, intensity is essentially gone. But if we could do this, if we are in a situation where, in this case, we have the magnetic sublevels here of the ground state, the -1/2, the +1/2, and they're equally populated. Right? 50% molecules here, 50% molecules here, essentially. So we have kind of a Boltzmann distribution where it's completely in an equilibrium, 50-50. Now if we would do our MCD experiment, we would get as many molecules here as here, so we get equal intensities for these two transitions, but because we're in a magnetic field, you can see the red arrow is longer than the blue one, so it takes a little bit more energy for the red transition than the blue transition. And so if we would now look at this, this actually should look like an A-term signal under these hypothetical conditions. But that's not usually how we do it when we do MCD. And again, this would require very high temperatures when usually the signal is extremely weak. So what we really observe is this case here, where we are at low temperatures and stronger magnetic fields, and now there's a difference in the Boltzmann population of the sublevels here. Again, this is the simplest case, S equals 1/2, so we split this into a -1/2, a +1/2 component, and now we observe difference in Boltzmann population of these two levels. Right? Then what's going to happen? Well, the transition probability for red and blue, of course, does not only depend on the intrinsic transition dipole moment, which actually should be the same since these are electronically the same states. But the transition probability also depends on the number of molecules that are in that given state. And there are more molecules here than here. That means we should get more transition and more light absorption here than here. And so in this situation, although these are the same states, so the intrinsic electric dipole moment, the transition dipole moment should be the same, the curves do not cancel each other because of the different in Boltzmann population. Right? We have a lot more molecules in that magnetic ground state of the ground state, so the red curve is a lot larger than the blue one. If you take the difference, they don't cancel each other out, and we end up with this green line here, and we end up with a absorption band shape for the C term. So that arises from the difference in Boltzmann population of the magnetic sublevels of the ground state. Right? And so if we measure now our MCD intensity or C-term intensity as a function of the magnetic field strength and the temperature, we can observe the changes here in the population of these levels of the ground state, which is similar to a magnetization measurement. But now we detect this optically by looking at how the MCD intensity changes as a function of temperature and field. So we're not measuring magnetization, we're measuring this optically, but we're measuring something that is equivalent to that. So this is really the important part for us. The C term is really the powerful part because the C term contains now all the information about the ground state. Right? And that's really the part that's interesting. And it's selective for paramagnetic sites. We can look at paramagnetic metal sites in proteins. So that's why we focus on this. And the C term also has by far the largest intensity at low temperature. So C term is temperature and field dependent. However, now C terms will saturate. That's something that's not part of the Stevens equation. Stevens equation, everything is linear. But if you just think about this, right, let's go back to that picture. Think about this logically. And as you increase the field and lower the temperature, at some point you arrive at a situation where you have this upper level here completely depopulated. All your molecules are now here, and no molecules are here. That means there is no more blue transition. There are no molecules in that state, right? So that means the blue curve is gone, and we only have the red curve. And if you take the difference, the red curve equals the green curve, right? Okay. So how can you get more intensity than that? You can't, right? So at some point, you can't go up linear in the intensity with the field. At some point, it has to stop, and you have to reach saturation when these upper magnetic sublevels, in this case it's only one, are completely depopulated. That's the end. You can't get more intensity than that. And so this is an extension then of Stevens' equation that actually requires that C terms will saturate if you go to high magnetic fields and very low liquid helium temperatures. I'll show a picture of this in just a second. Here's a couple of other things. Again, this is kind of a summary here. If you go to liquid helium temperatures, because of the 1/T dependency, the C terms are usually 2 to 3 orders of magnitude more intense than A and B terms. So these are really the signals to look for. These are very weak, and oftentimes, especially in low symmetry sites in metalloenzymes, they're not observed at all. So if you take a non-heme ion center, just a mononuclear non-heme ion center, you warm this up, you don't see any A or B terms at all. So for porphyrins, these are, as I mentioned a couple of times now, these are observed, but they're very weak. And then one other thing that is very important, if you think about a system like a non-heme ion center, right, this is in a low symmetry environment, you don't really have orbital degeneracy, neither in the ground state nor in any of the excited states either. So if all your states are non-degenerate, then, as I will show you in a little bit, you actually need spin-orbit coupling in order to induce MCD intensity. Spin-orbit coupling is important, and the MCD intensity scales with the amount of spin-orbit coupling between either your ground state or your excited state and another auxiliary state. This is the part we're going to talk about in just a little bit. So if that's the case, though, just to introduce this concept here, that gives you a very interesting selection rule, right? So if MCD C-term intensity scales with, in some way with spin-orbit coupling, that means if you have light elements, like in your ligand, carbon, nitrogen, oxygen, they have very small spin-orbit coupling constants. So if you have something like a pi-2-pi star transition of something like an aromatic system, even in a paramagnetic metal complex, MCD intensity should be very small. On the other hand, if you have a DD transition, a metal-based transition, right, where the ground state, so the orbital that contains that electron that you're going to excite is a metal-based orbital, the target orbital is a metal-based orbital, so we could say we have a lot of metal character in the transition, you should get a lot of MCD intensity, or C-term intensity, because the metal has a much larger spin-orbit coupling constant, right? A couple hundred wave numbers or something like this. So this, of course, is exactly opposite what you have in absorption spectroscopy, where your pi-to-pi star transitions in your aromatic system are most intense, and your DD bands are really, really, really weak because they are symmetry forbidden or Laporte forbidden. So you kind of have an inverted selection rule here in the MCD. So this is the first thing that's useful, right? So if you take your compound, you take an absorption spectrum, you take an MCD spectrum, you can compare them. You can get some idea about what the nature of these transitions is that you're looking at. So here's just one example. This is a copper complex we studied a while ago. It's just a copper-2 complex, very simple, S equals 1/2, with a trisposal borate ligand, and then here is a nitride bound to it. And then here, if we compare now the absorption spectrum on the top, and here these are the extinction coefficients. You can see here are the DD transitions. Extinction coefficients are around 100. So these are very weak transitions. And in solution, you can hardly measure them. We make a very, very concentrated solution. These are actually measured in the solid. And then here you can see that so the D transitions correspond to this scale in extinction coefficient, and then the rest of the spectrum correspond to this scale. And then you can see here are some transitions now, about 500, 1,000, and then it goes up from here. If we go to the pi to pi star transitions of these pyrazole ligands, now your intensity shoots up. And here's your MCD spectrum, where now your DD transitions are actually the most intense here, especially this guy here, number 3. And then here, this is the charge transfer region. You can see there are some decent transitions here. And as we go up, intensity dies off. So your selection rule is kind of opposite to what you see in an absorption spectrum. So that's already a pretty useful property. So in this sense, MCD is complementary in that way to absorption spectroscopy. The other thing is, of course, resolution. And as you've seen here, oh yeah, this is actually the first MCD spectrum I'm showing, right? So, of course, it's something that, of course, is intrinsically clear. But just to underline is, of course, MCD is like a CD spectrum. It has a sign, right? So you can have transitions that are positively signed, transitions that have a negative sign. And what that allows you to do is just get a much better resolution of optical transitions, right? If everything is positive and ends up, maybe you end up with a big absorption band, like a big block. But if some of them are positive, some of them are negative, you can just identify individual transitions much better in this case. And here's just one example that shows this. This is something we've been doing with the Pecoraro group, and they make these alpha helical coiled peptides. And this is just an example with a cobalt, a cobalt 2 center bound here. And it's a high-spin cobalt 2 center. So it's paramagnetic, and it has a bunch of DD transitions. And so this is the absorption spectrum now in the range where you observe DD transitions of that cobalt center, right? And this is still a pretty good case because you can actually identify some individual transitions here, but they made a variety of these types of systems, and in some of them, this is all just a big kind of envelope, right? But then if you look at the MCD spectrum, because you have the sign now, positive and negative transitions, you can much better resolve individual components now, individual transitions within this big envelope. So these are already two advantages of MCD spectroscopy that at least complement absorption spectroscopy. And we haven't done anything now at this point with magnetic saturation and all this crazy stuff. We haven't done anything. We just took an MCD spectrum just to look at optical transitions, what is their nature, and just resolve absorption spectra better. And so MCD is already good for doing these kinds of things. Okay, so now let's move on and look at this a little bit more closely. So from the Stevens equations, we have seen the Stevens equations are good, and they describe kind of the linear range where MCD intensity is linear with field, but just by thinking about this in a logical way, we realize that that's not the whole story, and that C-term intensity will saturate. It has to, just by thinking about how the C-term mechanism works. We need to move on. And this is something that was done here in Ed Solomon's group. Actually, Frank Neser was the guy who worked this out. So he went on, he took the Stevens equation, and now he put in Slater determinants and actually started to really write it all out and calculate what are the contributions, and assuming here non-degenerate states, ground state, excited state, all non-degenerate, so kind of a bioinorganic problem like a non-heme ion center in a protein where there is really not much symmetry left to look at. So assuming all the states are non-degenerate, and so he worked through this. And I don't want to torture you with this, so let's just look at the result of this heroic effort. So what do we get at the end when we do this? And this is shown here. This is the equation just for an S equals 1/2 system. This is the C-term intensity. And in an S equals 1/2 system, just as a reminder, there is no zero-field splitting, of course, right? But so the only magnetic anisotropy we can have is the anisotropy of the G values, or G tensor. So if you look at our sum here, the sum runs over U, V, and W, which are representations of just X, Y, and Z, so the 3 directions in space. And then we sum over the G value, Gx, Gy, and Gz. Right? And so reflecting the magnetic anisotropy or potential magnetic anisotropy of the ground state. And if we look at the central part of this equation, there are 2 of these triple products here, one here and one here. And this is really the important part here, these triple products. So these M's are transition dipole moments, and if you look at this nomenclature here, this will be a transition dipole moment for a transition between our ground state A and an auxiliary state K in the direction U. And again, U is either X, Y, or Z. we have a vector product of this with the electric dipole moment of the transition from A to J, but you see the direction has to be different. This goes in U, this goes in V, and then that's multiplied, scalar multiplied with a reduced spin-orbit coupling matrix element, which is called L. In this case, couples K and J. I'm going to show you some, again, graphic representations of this. I think then it will always become clearer than just looking at the equation. Right? But again, this requires some sort of orthogonality between the the transition dipole moments between these two transitions and the spin-orbit coupling. You can see all that happens in the three different directions. Again, it relates back to what I mentioned before, the very strict MCD selection rule. And also you can see there are two different contributions that vary in spin-orbit coupling part here. So who spin-orbit couples with who changes here. We'll look at this in just a second. And you can see what I mentioned before, spin-orbit coupling is required for C-term intensity. So in this case, with all non-degenerate states, if spin-orbit coupling is 0, so if these states don't couple, L is 0, then everything is gone, right? And our intensity is gone. So spin-orbit coupling takes the center stage here in this kind of situation. So this is then what we call the selection rule for MCD spectroscopy, that we have to have two transitions with polarizations that are orthogonal to each other, so U and V, and then we have to spin-orbit couple the states in the third direction in space, again orthogonal to that. And only if that is fulfilled, so we have two transitions with these properties, and they couple via spin-orbit coupling, only then will C-term intensity arise. This is our strict MCD selection rule. So if you look at this graphically, right, so let's look at the two mechanisms here. We can call this mechanism 1 and mechanism 2, representing these two parts here of our equation. If we look at mechanism 1, you can see we have coupling between K and J, and remember, we're still using the same nomenclature for our state. So A is still the ground state, J is our target state, so we want to look at this transition here from A to J, and then we need an auxiliary state K. And so in this case, we have to have spin-orbit coupling between J and K in this part of the equation. On top of this, we have to have orthogonal transition dipole moments for the transition from A to J and A to K. So these transition dipole moments have to be orthogonal, and then the coupling, again, has to be orthogonal to these two directions. So back to this picture here, right? Everything has to be orthogonal to each other. And if that's not fulfilled, then there's no MCD intensity. So if, for example, let's say this transition is X polarized, this transition is Y polarized, but they cannot couple in Z direction, then there will be no intensity. If these two states can couple in Z direction, but both of them are X polarized, there will be no intensity. If this couples in Z direction and this transition is Z polarized, there will be no intensity. Right? So everything has to be orthogonal, and only if that is fulfilled will MCD C-term intensity arise. So this is a pretty strict selection rule, actually, that we have here. So this is one mechanism. You can see here excited state spin-orbit coupling, now we could call this. And then in the second case, we just have the auxiliary state now not being close to our target excited state, but now the auxiliary state is close to the ground state. So now we do spin-orbit coupling between A and K, and both of these possibilities are legitimate and are reflected in these two parts of the equation. So the graphic representation hopefully clarifies these two mechanisms. Maybe at this point I should quickly ask if you guys have any questions, because this is pretty important as we go along and try to understand C-term spectra. Yes?
Do the components need to be perfectly orthogonal, or does there only need to be a component that is orthogonal?
There only needs to be a component, right? Because this is essentially vector algebra. But of course, the smaller your component, the smaller your intensity that arises. But yeah, that's true. All right, then let's move on. So here would be then an MCD spectrum of an S equals 1/2 system. On the left is what we would measure. So we take our system, and in this case, we ramp it down to the hypothetical temperature of, and actually this is derived from real data. This is derived from a copper complex that was done at 2 Kelvin. So we keep the temperature now the same, and now we start changing the magnetic field, and we measure our C-term signal. And you can see here's our C-term signal as it comes up. Here's our relative intensity, so we just normalize it to a total intensity of 1. and then we go up, and then at some point we reach saturation. And you can see when you go from 1 to 2 Tesla, here it looks like the intensity doubles, and then it starts to saturate. So if we plot this now in the form of a magnetic curve, so we plot this against beta H or beta B over 2 kT, like a Brion curve, and then we plot up the intensity, you can see, wow, this is a magnetic saturation curve that we have here measured. A perfect magnetic saturation curve. So our MCD intensity follows this pattern. And again, it's because we have the Boltzmann distribution, right, over the ms minus 1/2 plus 1/2 levels of the ground state, and as they split more, we change the Boltzmann population. We follow that difference in Boltzmann population. That's our magnetization. Right? The magnetization arises from this difference in population. That's where the C-term intensity comes from. So the C-term intensity directly relates to the magnetic properties of the ground state. And I think we can see this here. This is, again, just our picture of these two different components here. So there is actually saturation. So if we look at this curve now, we can then go and we can distinguish these different regions, right? So we can distinguish a Stevens region. So initially, we have a linear relationship between the intensity here and the magnetic field, just like it's expressed in the Stevens equation. But as we keep ramping and ramping our big fat magnet, we kind of get to an intermediate range here, and then we get into the saturation behavior. And we can describe this curve perfectly with a Brion curve, as shown here, that we use in magnetic susceptibility. So the tangents hyperbolicus of G beta B over 2 kT. So now you know why we plot this against beta H or beta B over 2 kT is because this is the way we plot our magnetic saturation curves, our Brion curves, right? So it gives you the same curve as we get from magnetic saturation. With a linear range, and we have this saturation behavior here. So we can go now, and we can now optically detect magnetic saturation curves. And so just think about what the possibilities are of this, right? If you have a mixture of two things, you went to the lab and made an ion complex, but there is a difference in the way the ligand bound, and so some of it is low spin and some of it is high spin, and you have it mixed. Now, if you measure magnetic susceptibility, you just get a conglomerate of this, magnetization of the two. If you measure an MCD spectrum, you will see in the spectrum there are some bands that arise from the low spin component, some bands arise from the high spin component. If you pick a band for the low spin component, you measure the magnetic saturation, you can show this band belongs to the low spin component. And you take another band, you measure magnetic saturation, you can show this one belongs to the high spin component. And you can individually get the magnetic behavior of these two, although they're mixed. As long as you have individual bands for each component, you can sit on that band and you can measure the magnetic behavior of that in a mixture. Right? So just think about what the possibilities are. Because we detect this optically, not by measuring the bulk magnetization of a sample. Okay, so if we look at this further, like Brion curves describe the magnetic behavior as a function of the spin state. And so this is something you can find in textbooks about magnetic susceptibility. So this is a plot. This is the magnetization plotted again over beta H or beta B over 2 kT. And then you can see that the magnetic response will, of course, change as you change the spin state. As you put more spin into your sample, you get more magnetization. So if you have a sample, you measure magnetic susceptibility, you could look at the height, right, the amount of magnetization of your curve, and that will tell you now what the spin state of your compound is. Now in MCD, unfortunately, it's not that easy because, remember, in the C-term equation, right, the MCD intensity is a conglomerate of the magnetic properties and the Boltzmann distribution on one side, but of course the electric dipole transition moment also is in there, right? So there's also an intensity component for your transition, and both of them together give you the C-term intensity. So you can't look at the absolute intensity of a C-term signal to get the spin of your sample, right? That's why we normalize the intensity, and that's what I had done on that previous plot. Here, we take the maximum intensity that you can get, so lowest temperature, highest field that you have in your system. When the intensity saturates, that's your maximum intensity. You set that to 1. You have to normalize to that intensity. So if we do this now, then you can see that, well, then we normalized all these curves to the same height. So obviously that information is lost in the MCD. That's what makes it easy to magnetic susceptibility. You get the spin of your compound. Now it's more complicated here because the magnetic properties are convoluted, right? They're convoluted with the optical properties. But what we can do is now, we can look at these Brion curves, and if we normalize all these Brion curves to the same value, 1.0, and you plot them, you'll see that they are not the same. They don't superimpose. They have a little bit of a different shape. The more, or the higher your spin value is, the more quickly they rise, and then they saturate, right? So the shapes of the curves are different. And so what we could do then is, in the MCD, since the height or the intensity is arbitrary, we could look at the slope of these curves, and we could try to determine the total spin of a sample in this way. And here's one example where this worked. This is a complex we studied in collaboration with Frank Meyer from the University of Göttingen. This is the famous Siamese twin porphyrin. It looks very innocent when you put it into ChemDraw, but then once you get a crystal structure, you see that thing is really, really twisted. And in this complex here, we have 2 copper 2+ in there. Right? Each copper is 1/2 spin, so you can couple them either to a spin 0 or a spin of 1. And you would think, well, they should be coupled pretty strongly if you look at your ChemDraw, but if you look at the crystal structure, maybe not, right? Because they're completely torqued against each other. And in fact, the coupling between these 2 copper centers is pretty weak, but now we do our MCD, and we plot our Brion curves. So this is what's shown in the back here in the fine line. These are the Brion curves, s equals 1/2, x equals 1, and so on. You can see they're all normalized to 1 now, but you can see the slopes are different, right? Now we take our saturation curve for our copper compound, which is the fat line, and you can see the fat line superimposes on the s equals 1 line of the Brion curve. So that means that MCD says the spin of this is 1. It has a spin of 1 ground state. So this is pretty good, but unfortunately, most of the time it doesn't work like this. So this is kind of a nice case here. And the real problem here is, of course, zero field splitting. And again, as you can see, I'm constantly referring back to Frank Nese's lecture on ligand field theory, because this is really the foundation of all the things we're talking about here, right? Electronic structure in transition metal complexes. The easiest way to understand this is ligand field theory and NMO theory. So zero field splitting is an effect that we've seen a couple of times coming up. And so I don't want to spend too much time on it, just very quickly. What is zero field splitting? And Eckert did a really nice job explaining that. So here's just a quick nutshell. So if you just take an example, high spin ion free, S equals 5/2. If there's no zero field splitting, we can see that all these spin sublevels of the ground state have the same energy. They degenerate. And then as you introduce zero field splitting, they start to split. And again, importantly, they split in the absence of a magnetic field. There's zero field splitting, right? So we don't need a magnet to get this. And if we have a situation like this, then our magnetization or saturation curves will not overlay anymore in this nice fashion that you saw here, right? And so you can see this is not just one curve. You can see these are several curves, right? You can kind of tell here, but they're all superimposed. They're measured at different temperatures. But if you have an S equals 1/2 system, or here's a case, we have 2 copper, 2 S equals 1/2. There's very, very small zero field splitting in that system. The curves superimpose. Now we can play this trick with the Brion curves. But the Brion curves, of course, the Brion curves require this situation here. This is how they're derived. Right? The Brion curves are derived from the situation where all these sublevels are actually degenerate. But if they're not, what happens if they're not degenerate? Well, if you look at a case like this, your magnetization curves do not overlay anymore. For the different temperatures, they're offset. We call this nested. These magnetization curves are nested. Right? And so here we have a case where D is just arbitrarily chosen to be -1. E over D is 0, so it's an axial system. We're looking at an XY polarized transition, and then you would measure something that magnetization curves that look like this. Here's a 1.5 Kelvin one, here's a 25 Kelvin one. Now you can imagine if you take this, right, something like this, and you put that on this plot here, well, that doesn't look very good anymore. You can't really tell, right? You can say, well, maybe I take the one at the highest temperature, we have the most Boltzmann population over the levels, but don't do it, right? So this doesn't work anymore in that easy way when you have zero field splitting in the picture, and you get the nesting. On the other hand, of course, if you're thinking about extracting now information about the ground state of your system, the magnetic properties of your system, this nesting is actually good. Because this nesting changes in a very dramatic way when you change the magnetic properties of your ground state. So that actually helps you, in a sense, to better fit your data, or you get a more unequivocal fit of your data when you have this kind of nesting. So that's also important. Okay, so just one more step here. So we looked at the MCD equation for the S equals 1/2 case. This is a special case of a more general equation that is shown here. So the general equation for MCD intensity for a system where spin is larger than 1/2. So the S equals 1/2 is a special case of this equation here. And that was derived back in 1999, again, as I said, by Frank. And so you can see he was really happy about this when he was at ICBIC in 1999 doing a karaoke here. And he thought about this equation here that he was going to publish in that same year. So if you look at the equation, you will find the same things that we've seen before. But now, of course, if we have a spin larger than 1/2, we have all these magnetic sublevels of the ground state. Right? And so we'll have to sum over all these magnetic sublevels. And, of course, if you have a system that's rhombic, you'll also start to mix up these MS functions here. So in general, then, the spin functions of our ground state are linear combinations of these MS functions. And so we have, these are these theta i's here. So we sum over all of these spin functions of our ground state with 2s plus 1 spin functions. So this is what that sum runs over. And then this is the Boltzmann factor, right? So that tells you what's the boson population of that given magnetic sublevel of the ground state. So essentially the way you solve this then is you run a spin Hamiltonian calculation, right? That gives you all these sublevels. Then you run a Boltzmann population over them. And then you have this information here, and then you can go on. And then we have 3 components here. You can see this here, x, a y, and a z component. And L is just the Euler angle, so it's the orientation of the magnetic field relative to the molecular coordinate system. And then we're usually looking at samples of randomly oriented molecules. So we have to integrate over all these different orientations, just like what you do when you do EPR, and you have just a solution sample or something like this. So you integrate over all these orientations. That's what's in here. And then these M's now are our effective transition dipole moment products. And this is now where these triple products are hidden. So you already thought you get away from them, but they're still there. They're just hidden in these M's here. So if you look at these M effective transition dipole moments, there's exactly the same thing we've seen before, right? We have 2 electronic transitions, and then we have spin-orbit coupling in the third direction, and everything has to be orthogonal. So this will be the YZ effective transition dipole moment. So we have Y and Z polarized transitions, which then requires spin-orbit coupling to be in X direction. And then we have the 3 different components in space. And then we integrate over the whole thing because of our generally conditions that we have the solutions and samples of randomly oriented molecules. So we have to sum over or integrate over all these different orientations we can have. And this equation then is good because with this equation now we can go and we can fit our magnetic saturation curves. Now, if you measure the C term or the saturation curves for some new compound and you have no information and you want to fit them, though, that's a problem, right? Because there's a lot of variables that we have. Again, we have the magnetic properties of the ground state, which are reflected by the spin functions and the Boltzmann population. So they depend on G anisotropy, they depend on the D value, so zero field splitting, and they depend on the rhombicity. And then on top of this, we have all our polarizations here, the polarizations of our transitions on top of this. So in short, you can't fit everything at the same time. So what you need to have in order to do this successfully is you have to have either the information about the magnetic properties of the ground state, and then if you know that, you can go and fit the curves and get the polarizations of your transitions. Or if you have an idea what the polarizations of your transitions are, and that might sound absurd, but if you have a metalloporphyrin, right, you know that your pi to pi star transitions are polarized within the plane of that porphyrin. And the unique axis is usually orthogonal to that plane. So if you have a metalloporphyrin, you have a little bit of a better idea of what's going on. If you have an idea about the polarizations, you can fix those. Then you can determine the magnetic properties of the ground state. But you can't do both at the same time. But, of course, the magnetic properties you can get with other methods, right? You can do an EPR, you can do squid, you can use other methods to get to the D value, the E over D, and then you put that into the equation and you fit the polarizations, and that is what we usually do. Now think about it. These are samples, or you can also use Mössbauer spectroscopy to get to those. So you have several ways to get these magnetic properties. These are samples of randomly oriented molecules, but by fitting the saturation curves, if we know the magnetic properties, we get the polarizations. We get single crystal information, right? We can determine what the polarizations are in the molecular framework of all these electronic transitions for a sample of randomly oriented molecules by fitting the saturation curves, if we know the magnetic properties. And that is extremely powerful. So at this point, you could see that there's a lot of cool stuff you can do with MCD. So again, think about how that might be a useful technique for your research. So at this point, it's already past 10, so I don't know if I can get through all my examples, but let's go and look at some examples. At least you can get some idea of practical applications of MCD. So this is a picture. This is actually a picture of an MCD spectroscopist after measuring saturation curves for 24 hours straight on the way home. This is about what that looks like. So, some case studies on metalloporphyrins, we can just see how much we can do, and if you want more, we can always talk about it after the lecture or later over a glass of beer. It's my preferred method to do science. So, now we're talking about porphyrins, so just very, very quick. This is, first of all, the aromatic core of a porphyrin, and then nature uses all kinds of variants of the porphyrin that just differ in the substitution pattern in the periphery of the porphyrin, but you guys are all bioinorganic chemists, you all know this, so we don't have to dwell on this. Different forms of this heme are used in nature, and then we need to kind of understand the basic electronic properties, and we can explain this with the famous 4-orbital model that was first constructed by Martin Gauterman. And essentially, we're looking at 4 orbitals here, as the name implies, and these are pi orbitals of the porphyrin ring. You see, there's no metal there. You don't need a metal to do this. So 2 pi orbitals that are occupied, one of A1U, one of A2U symmetry in D4H. And then we have this LUMO here, and you can see the LUMO is twofold degenerate. Ooh, and that smells like atom intensity, right? That's where the atom intensity comes from. The LUMO is an EG-type orbital. We have 2 components here. Now, this is our situation, and now we do electronic excitation. And so if you do that, right, you can excite an electron from A1U or can excite an electron from A2U into the EG. So HOMO, LUMO, or HOMO -1 LUMO transitions. That will give you 2 excited states for both of these transitions. And if you do the group theory, you can easily see these excited states, psi1 and psi2, they both have EU symmetry. So right, they are twofold degenerate. Now, in the porphyrin, this is interesting. These couple now very strongly. They couple via configuration interaction. Ci. And that gives you 2 states now. And the one state at higher energy, we call or not everyone, but most people call this the Soré state. And it's the positive linear combination of these 2 states. And then we have what we call the Q state, which is the negative linear combination here, so plus and minus combination of them, that result from this mixing here of these 2 states. It doesn't change the symmetry, of course, right? So both Q and Soré states still have EU symmetry in overall D4H molecular symmetry. On top of this, we get vibronic coupling between the Q state and the Soré state. That gives rise to what we call QV, the vibronic state. And then if you know vibronic coupling, then you know this energy difference here corresponds to the energy of the vibronic coupling mode, which are porphyrin ring vibrations. So this difference in energy is about 1,300 wave numbers on average. Right? So this is kind of the pattern. And then if you look at a simple absorption spectrum of a metalloporphyrin, it looks like this. And so you can see these 3 states then getting excited. So here's the so-called Soré band. So the excitation from the ground state in the Soré state. You can see extinction coefficient is ginormous, 250,000. That's because the individual transition dipole moments of these components, they add up, right, in the Soré state. But in the Q state, they cancel. And so Q is very weak. And then here's QV, the vibronic component of Q. And this is, here you can see this is the red scale is for this part and the black scale is for this part. So you get, the Q is still about 5,000, but it's a dwarf compared to the Soré band. This is what these absorption spectra generally look like. For simple cases, this is a cobalt porphyrin. Okay, so now let's look at one example, how we can use MCD spectroscopy to learn something useful about some metalloporphyrins. So here we looked at model systems for high-spin ferrous hemes. And of course, you know high-spin ferrous hemes. So a ferrous heme with a bound, say, imidazole, this is kind of the active state of all kinds of globins. Hemoglobin, myoglobin bind oxygen, and then the whole family of globin proteins. And then they can activate or bind small molecules like this. So in collaboration with Bob Scheidt's group, we looked at two different versions of this, where we either bind an imidazole or an imidazolate. So the only difference is a proton, either with a proton here or no proton here. And we looked at the MCD spectra to see what the properties of these complexes are. So if you take the MCD spectrum of one of these compounds, this is the imidazolate complex, this is the absorption spectrum, this is the MCD spectrum. You can see the MCD spectrum is rather boring, right? So you have your Q state here, here's QV, and for each one you get what we call a pseudo-A, so it looks like an A term, and it has a negative and a positive component, but you can see that they are temperature dependent, so they're not really A term signals, they just look like them, so we call them pseudo-A's, but they are actually C terms in nature. And they correspond to the fact that these states all have EU symmetry, so they have two components. And the way they couple is then that if we look at the transition from A to J, for example, we get a positive signal, and then K is the auxiliary state. And if we look at the transition from A to K, now J becomes the auxiliary state, but the sign now of the intensity will flip. Right? So we can actually see in the MCD the pattern of transitions that belong together, because these excited states are spin-orbit coupled. It has a positive and a negative signal. And since the Q, QV, and the Serre band each have EU symmetry, we have these two components, and each one of them gives rise then to this derivative-shaped signal, where one component has a negative intensity, one has a positive intensity. So here would be Q, here's QV, and then here's the Serre band, and then this is an impurity because these complexes are air-sensitive as hell. And so it's extremely hard to keep them from oxidizing, so there's a ferric impurity down in the spectrum here. So this spectrum looks kind of boring, and that's what we thought. So we said, this project doesn't seem to get to too much interesting information, but then we looked at the imidazole, the imidazolate, and then also a chloride-bound complex, for example. These are all high-spin ferrous. But then we noticed that the spectra all look pretty much the same, but there's a huge difference in the intensity. If you look at the molar intensity of the Serre band, for the imidazole complex, it's about 5,000 per mole per centimeter per Tesla, and for the imidazolate, it's only 300. The spectra look the same, but the intensities are different by an order of magnitude, and the chloride is kind of a little bit in between, but still on the low end here. So how can we explain this? And so we can explain this when you think again about these intensity mechanisms. Okay, so these are high-spin ferrous hemes. So here's our little ligand field diagram. Ligand field theory, always a good way to start thinking about the problem, right? So we have a set of T2G orbitals, and they have 4 electrons in them. So we have one pair, and then we have 2 singly occupied orbitals. And then the EG's ones are singly occupied, but that is not going to be important here. So we're looking at this part. And now if you think about the MCD mechanisms, of course, let's go one back. We know that these states, so if we take this red electron, we excite it. We can excite the red electron here or here. Right? These excited states, these are ligand field excited states, are very low in energy. They're very close to the ground state. Right? And so that kind of implies that besides having the usual intensity from this kind of type 1 mechanism where we have spin-orbit coupling of these Serre excited states, maybe we can get some intensity here if the ground state could couple with low-lying excited states that we could generate by exciting this red electron to these other 2 T2G type orbitals. Right? So this will be a mechanism 2 type situation where we have low-lying ligand field excited states, very low. They could be just 500 or 1,000 wave numbers above the ground state. So they are close enough to strongly couple with the ground state. So if you think about this, then in this framework, there are 2 different cases that are possible. In one case, we put that extra electron into the dxy orbital. It's doubly occupied, and the xz and the yz are singly occupied. Or we put that extra electron into either the deoxy or the divisy orbital. That will be equivalent. We'll just show you the deoxy orbital, and then we would have a situation like that. And so now we can think about this situation, how that would relate to MCD intensity using the selection rules that we know. Right? And so we know that the Sorey band, or the Q bands, are all in-plane polarized. Right? These are pi to pi star transitions. Charge is moved around within the plane of the heme. So they're X and Y polarized. So that means spin-orbit coupling has to be in Z direction. That's the only possibility to get MCD intensity. Right? So if we have a situation where the ground state is dxy, and we now excite that electron here, well, dxy cannot spin-orbit couple with the deoxy or divisy in Z direction. Spin-orbit coupling matrix elements for this are all 0. So in a situation like this, there will be no intensity arising from this mechanism, not for spin-orbit coupling in Z direction. On the other hand, if you look at mechanism 2, if you look at case 2, here, of course, the deoxy and divisy, they are strongly spin-orbit coupled in the Z direction, right? Spin-orbit coupling or L operator rotates orbitals around, and you can rotate along the Z direction, XZ into YZ. So they couple strongly by spin-orbit coupling. So that means in this scenario, there should be extra intensity arising from this mechanism too. And that now implies that if we take our imidazole complex and we take the proton off, we change the ground state of our heme. We shift the electron around between case this and a case like this. So the extra electron could either be in the plane of the heme or it could be orthogonal to the plane of the heme. And we can change this by deprotonating that imidazole ligand. So that's pretty interesting. So this was the assumption, right? And so we looked at some DFT calculations to see what the theory would tell us. And to our greatest surprise, actually, the DFT calculations predict that too. So if you look at the imidazole complex, and you know, these are only the beta orbitals, so this is just a spin down. You can see in this case, our single electron sits in a DXZ orbital, orthogonal to the plane. That's the case where we can get that extra spin-orbit coupling, the extra MCD intensity. That's the case where we measured the 5,000, the really large MCD intensity. And if you now deprotonate your imidazole and go to imidazolate, where is it here? Now this singly occupied orbital corresponds mostly to a dxy. It's not exactly in the plane. It's a little bit tilted out of the plane, but it has a dominant dxy contribution here. Right? So there's a change in ground state, and that's reflected by the absolute intensity of your MCD signal. And of course, this is important, right, in biology, as we're thinking about histidines binding to metalloporphyrins. We have a situation like in the globins where people generally believe that we have weak hydrogen bonding here. So you would say the proton sits on the imidazole, right? So that would be an analog to our imidazole complex, whereas in peroxidases, there's a lot of speculation that that histidine actually could be partially or fully deprotonated, making this an imidazolate, and that would actually change the properties of our ground state. I don't want to dwell too much in this, since this is an MCD presentation. Okay, and so we have about 10 more minutes, so let's look at some high-spin ferric hemes. High-spin ferric hemes has way more interesting MCD spectra than these high-spin ferrous ones. You can already see that there's a lot more going on by just looking at the absorption spectrum. This is a model complex. This is just a ferric tetraphenylporphyrin chloride complex. Here's a picture of this. Right? And you can see, oh, wow, there's a lot going on in this absorption spectrum. Now, you might think that we've gone completely insane here if you look at this fit, right? To say, what are they doing here? But if you take the MCD spectrum, you can actually identify all these different bands. But before we go there, it makes sense to kind of take a step back and think about, right? So in the simple metalloporphyrin spectrum, there are only 3 bands, right? There's a Q band, a QV band, and the Sorey band. But there are more than 3 bands here. So we take a step back and think about what could all these other signals here belong to. Now, this is a high-spin ferric heme. And again, pointing you to Frank Neese's talk, remember, any kind of ligand field transitions, there requires a spin flip. So it's doubly forbidden. So we're probably not going to be seeing DD transitions in this spectrum. If it's not DD transitions, it could either be other types of pi-to-pi star transitions from the porphyrin, or, of course, charge transfer, right? Charge transfer transitions. So what we did first is we ran a TD-DFT calculation to just get an idea of what kind of states could, or what kind of transitions we could actually observe in the visible range of the spectrum. And this is just an overview that just shows you what these are. Don't look at the details here. So we have pi to pi star transitions of the porphyrin, which includes the Q and the Sorey band. We have porphyrin to ion charge transfer. And remember, we have a high spin ferric heme. Every d orbital is singly occupied. That means every d orbital could function as an acceptor for an electronic transition. Right? There's a magnitude of charge transfer now we can do between just the porphyrin and the ion, because each orbital is just singly occupied. So there's all kinds of these guys. And then we have transitions, of course, between the ion and our axial ligand, so chloro to ion charge transfer transitions. So how can we distinguish them, right? So here we are. We have a magnitude of transitions. We're scratching our head now, and it's like, what can we do now? So in this case now, the polarizations come in handy, right? Looking at polarizations of these electronic transitions. And that will help us to assign the spectrum. So in order to do this, we have to go now and measure the saturation behavior of all these different bands. We know the magnetic properties of the ground state. They're actually known since the 70s. People have looked at this complex for a long time. We know what the D value is. We know what E over D is. And the G values are pretty much 2. So these things are known. So we know that we can stick this in the equation. We can fit the polarizations. Okay. Oh, one more thing is, of course, what we fit is just the C-term intensity, not the total MCD intensity. So here's a picture. This in black, this is the MCD spectrum at 5.8 Kelvin. You can kind of see this here. And then we took the same sample and we warmed it up to room temperature. And remember, the C-term intensity is inversely proportional to temperature. So at room temperature, C-term intensity is completely gone. So we go to the spectrum in red, in dashes. This is now an A and a B term spectrum, right? Because those are not temperature dependent. And so you can see that there is actually an A term here in the region of the Sorey band. And there's pretty much nothing else. If you zoom in, you can see a little derivative here for the Q band, but that's pretty much it. So you can see that if you take the difference, the black spectrum and the different spectrum are pretty much identical, except there's a small difference in the region of the Sorey band. So these are the relative magnitudes of C-term intensity versus A and B-term intensity. So as I said, the C-term is a dominating intensity mechanism for anything paramagnetic. And so you can see this here right away. Now, when we fit our MCD intensity, we fit the C-term intensity, so we have to fit our difference spectrum, the intensity after subtracting out the A and the B term, the temperature-independent part. All right, so then we can look at our spectrum, the MCD spectrum, and we can now go and get saturation curves for all these different bands and see what the polarization is, and we can fit them. And so here, for example, this feature number 3, you can see has this very strong nesting, and this is actually XY polarized band. So this is a charge transfer between the porphyrin and the ion center. Now, as we move through this region, we see some Z polarization coming up. And in this particular case, Z polarization, so again, these are transitions now between the ion and the chloride, right? Axial transitions. They show up by a reduction here of the nesting in these curves. So there is some Z polarization in this region here. But there is no particular band you can pick out in this region. So that means that the chloro to ion pi charge transfer is not identified with a single band, but there's a couple of bands here that have some of this charge transfer character. But there is not a single band that is fully Z-polarized. There's a couple of bands that are partially Z-polarized. And of course, in a complicated situation like this can happen. So the chloro to ion pi charge transfer is kind of smeared out over a couple of these transitions here between 15 and 20,000 wave numbers. And then at higher energy, so we can now complete all this picture, right? And we can essentially assign these polarizations. So we have some blue bands here that have partial Z-polarization, and there's band 14 here, which is strongly Z-polarized. This now is the chloro to ion sigma charge transfer. And if you look at this spectrum here, this absorption spectrum, of course, the most striking thing here is this big, broad shoulder here, which is normally not observed for metalloporphyrins. And so this shoulder actually arises from the chloro to ion charge transfer transition. And we can show this by looking at the polarizations of our C-term signal. Okay, so now we're kind of running out of time, so we're going to take a little jump now. Well, after we had established that this actually works and we can identify actually polarized transitions by their saturation behavior, we now took this over to a cytochrome P450. This is P450 CAM. And in particular, in this case, we have this famous cis pocket. So there is this hydrogen bonding network kind of wrapped around the axial cysteine ligand here. And people have been speculating for a long time what the roles of all these hydrogen bonds could be. And so we wanted to look at ideally identifying the sulfur to iron charge transfer, and then we wanted to look how iron-sulfur bonding changes when you change that hydrogen bonding network, right? By looking at mutants where you remove some of these hydrogen bonds. So that was the goal of the project. Here for our MCD talk, of course, the important part again is that we use this polarization information to get at this information. Okay, so let's speed it up a little bit. One of the complications here is that in this tetrophenyl porphyrin compound, of course, we have a high symmetry heme. A porphyrin with just 4 phenyl substituents gives you pretty much nice 4-fold symmetry. But, of course, here in our naturally occurring heme B, we have a lower symmetry, right? So we have these 2 propionate substituents and so on. And this is directly reflected in the EPR spectrum. For the TPP complex, you get a perfectly axial EPR spectrum. E over D is dead on 0. And here E over D is 0.087 for cytochrome P450 chem. That was determined way back. And so you can already see there's rhombicity. That tells you there's some low symmetry going on, right? There is some, the heme doesn't quite feel like D4H anymore. It can feel that there is this unsymmetric pattern of substituent. So the first question is, does our methodology actually work for a case where you lower the symmetry? So X and Y are not symmetry equivalent anymore. So again, we went to the spectrum. Here's the absorption spectrum here on the top. This is the MCD spectrum. Again, emphasizing this idea. Look at this spectrum here, right? This is just some kind of slope going up. So how can you even identify transitions here, individual transitions? Well, if you look at the MCD spectrum, it beautifully shows you all these different components here of these different electronic transitions. But that's not the point here. So we looked at magnetic saturation curves, and we predicted what these curves would look like. And to our greatest excitement, the same thing we saw before also holds here. So whenever you have a case where you have Z polarization, you can see that this nesting starts to go away when there's more and more Z polarization. And this case here, this is a situation where you have 50% X and 50% Z polarization. You have no more nesting at all in these curves. So again, the curves are sensitive to Z polarization, but not as strongly as in the purely axial case, but we can still use the methodology. So we can do the same thing. We can walk through the bands, and we then found a very similar situation as in this model complex, where here in that low energy region, right, we have bands that are mostly XY polarized, but they have some Z component to them. So band 2 here has about 10% Z character. And then you can walk through the bands with the same mechanism. And so just like before, you observe that the sulfur to iron pi charge transfer, again, is smeared out over a couple of these transitions. There's no individual transition you can pinpoint for that. There's a couple of transitions that have 10 to 20% Z polarization in them, but no distinct transitions. This is the region of the pi charge transfer. Something that's very striking here in the MCD spectrum, if you look at the higher energy region, you look at the spectra I showed you before, the Sorey band is usually also gives rise to the most intense feature in MCD, and that's because it has this ginormous extinction coefficient of 200,000, but not here. There is this guy here, number 13, right? The troublemaker shows up. It's way more intense than actually the Sorey band. And if you remember, we talked about the intensity mechanism, right? Intensity scales also with spin-orbit coupling. So the fact that there's this huge band here implies it is a band that has metal character. And it's probably arising from a charge transfer band. And it's in the right region where we would expect our sigma charge transfer. Right? So that looks pretty promising. And then we measured the saturation behavior of this one, and it has no nesting in it. So it has about 50% Z polarization in this band. But we don't believe that this is, again, a pure transition, that you can say this is the sulfur to iron charge transfer. It is a band that has a very large contribution from this, but there are certainly other contributions in there too, mostly porphyrin to metal charge transfer, which is probably mixed in with this transition here, giving you this kind of overall mixed XZ polarization of this feature. So we have this band then. We went on to, this is just a summary, but we go a little bit faster now. This is the low spin case. So we're looking at the high spin state here. The low spin case, you can see, looks completely different, a lot more MCD intensity. And then here we just have the Sorey band now, again, being the dominant feature. But the important part here is if you look at the low spin case, this big, intense negative band at about 28,000 wave numbers is completely missing. Right? So this band only shows up in the high spin case. And that's important because in some of these cytochrome P415 samples in wild type and also some of the mutants, when you bind substrate to them, they are purely high spin at room temperature. When you cool them to cryogenic temperatures, there's a fraction of low spin that will form. And in the Sorey region, the low spin component is way more intense than the high spin component. But of course, we're interested in looking at this charge transfer, and the low spin does not have this charge transfer. So even if we have a mixture of high spin and low spin, we'll still be able to clearly see that sulfur to iron charge transfer transition in this energy region, because the low spin complex does not have any intense feature there. So now let's do fast forward. So we looked at wild type and a couple of the mutants. Here's just an example of the wild type. So you can see it's a mixture of high spin and low spin, but here's our big charge transfer band. And then we can jump over this. And then we looked at the wild type, and we looked at 2 mutants where we removed hydrogen bonds. So we mutated our 358, which is this guy here, and then the Q360 here. And you can see that there's only a tiny, tiny shift in this charge transfer band of, I think it's like 100 wave numbers or something like this. So that indicates that these hydrogen bonds don't actually change the iron-sulfur interaction that much. And if you go back to the literature, of course, people have looked at this with Raman spectroscopy too, and if you look at the iron-sulfur stretch, and this is some work done in Morishima's lab, you can see the same mutants that we used, plus an additional one. You can see the shift in the iron-sulfur stretching mode is also tiny, 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 tiny. And so that implies that when you remove these hydrogen bonds, there's almost no change in the strength of the iron-sulfur interaction. So that gets me to the end. We can think about this now, what the consequences of this are. Right? And so if the hydrogen bonds, at least the ones that we looked at, we didn't look at all of them. So there's one that we were not able to make a mutant of. But if the ones that we looked at clearly are probably more there for stabilization of that thiolate ligand. The thiolate ligand, especially if you look at model complexes, is very susceptible, reacting with O2 and other diatomics. It can be protonated, it will fall off then, and then your protein degrades. Right? So these hydrogen bonds could be there to protect the thiolate ligand and maybe also place it in the right position to bind to the iron center. But they don't really tune the iron-sulfur bond that much. And then on the other hand, of course, if you also think about what actually cytochrome P450s do, maybe having lots of strong hydrogen bonds might not be even the best thing, right? Because if you think about the way people analyze cytochrome P450 reactivity, going back to the 70s, there's the famous push effect that John Dawson proposed, where the strong donation from the thiolate would help cleave the OO bond to make compound 1. Well, if you put a lot of hydrogen bonds on your thiolate, you will reduce the donicity of that ligand. So you will lower that kind of push effect. Now, the push effect, of course, has its followers. It also has its opponents. So I would say this is still somewhat controversial to how much of this is really there. But what we've clearly seen from Mike's work now recently is that if you think about hydrogen atom abstraction, right, if you think about driving force for hydrogen atom abstraction, that can come from redox potential or basicity, that's certainly having the thiolate there, making compound 2 very basic, right, will help with hydrogen atom abstraction. In order to get this effect, again, you need relatively strong donation from that thiolate ligand. It will make the iron 4-oxy unit more basic. It will give you more driving force for hydrogen atom abstraction. So there are some very interesting papers here. If you're interested in this, I encourage you to read. Very interesting. So you can think about now how this hydrogen bonding network relates to function in these systems. So you want some hydrogen bonding that you can do, and you can tune the iron-sulfur bond. And maybe that's the one we didn't look at. That's the strongest one. And then you have other ones there that maybe just protect that thiolate ligand and maybe also orient it right to bind to the iron center. So I would say this is still open for discussion. Okay, and with this, yeah, so we didn't investigate this mutant because if you do this mutant, the protein becomes extremely unstable. And so maybe that means that this is the one strong hydrogen bond that's actually used to fine-tune the properties of the iron-sulfur bond. This one we could unfortunately not probe. So that would be really interesting, of course, to look at this amino acid. So with this, I'm at the end. And I just want to highlight here the past and current students from my group who have done a lot of MCD spectroscopy. So Grace Gallinato is a former postdoc. She's now actually faculty at Penn State Erie, and she is here with us right now. So she did the cytochrome P450 work, and then Amy and Ashley are current graduate students in my lab. And if you've booked for the practical tutorial on MCD, then these are the guys who will teach it together with me, so we'll meet them there. And with this, I'm at the end, so I'm glad to see that most people are still awake. And thank you all for your attention. I'll take any other questions you might have.
Any questions for Nikolai? Yeah.
So if you're trying to distinguish whether you have a mixture of a paramagnetic and a diamagnetic compound, would you be able to distinguish those?
Well, you would probably not see the diamagnetic compound in your MCD, right? So you would only see the paramagnetic one.
Could we see the A and B term?
Well, it depends on what the compound is. So in a metalloporphyrin, you might get lucky, right? So if you have like a high spin and low spin iron 2, the low spin iron 2 will be diamagnetic, but it has very characteristic signals in the Q region. So in this case, you could. But if you have something like non-heme iron, or like mononuclear copper or some site like this, they don't have much A and B term intensity, so you wouldn't see them in your MCD spectrum. So it depends on what system you're looking at. But outside of hemes, A and B terms are usually really, really weak.